The next instruction is software interrupt instruction. A software interrupt instruction causes a software interrupt exception, and it provides a mechanism for applications to call operating system routine. So all of us know that interrupt will actually stop the normal execution, and it switches the control to an ISR. All of you know the term of ISR, interrupt service routine, a routine used to execute uh, the task when the interrupt arises. So here in ARM, we make use of software interrupt instruction called SWI. So when once we make use of SWI with an SWI number, again conditions, as I said, we have seen the conditions in the previous slides regarding the flags. That's optional, and coming with followed by SWI number. So whenever we make use of SWI software interrupt, these are the things that will happen. What is that? The link register it will be equal to the address of the instruction following the SWI. So what is that link register? Whenever we are switching from one main program to the sub program, the address of the next instruction, here SW is the current instruction, whatever is the next instruction, the address of that will be moved on to link register. So that will be stored in LR register. All of you know LR register. In the previous module, you have studied LR register. R14 is LR register that will hold the address. Now, what will happen to SPSR status register? That will be holding whatever is there in CPSR. And PC will be holding the address of the interrupt handler. This we will see vectors plus 8, we will see that. CPSR mode will become now, earlier it was in the user mode, now it will be going to the supervisor mode, that is processor mode, SVC. Now CPSR I, that is a flag I, will become 1. So it will mask that IRQ interrupt, so that others, when it is handling the current interrupt, it will not let other interrupts to raise. So it will make the CPSRI in the CPSR register, the I bit, it will make it 1, means it will mask the other interrupts from raising. So in this way, each SWI instruction has an associated SWI number, which is used to represent a particular function or call. So every interrupt will have a unique number, so that it becomes easy for the processor to differentiate among the interrupts. Based on the number, it will execute the corresponding interrupts. So just like the normal interrupts what we studied in computer organization. Now let's take an example. Let's take the current example here. This is a precondition. So this CPSR content is this. That is these flags, negative, 0, carry flag is all 0, overflow flag is 1, and saturation flag is 0. And right now interrupt flag is 0, means there are no such interrupts to raise. It is not masked as of now, and it's in the user mode. Now the PC is pointing to the address 8000, means this is the instruction it is pointing to. And link register is holding some address. Don't worry about this. It is holding some address as of now. And that always the link register will be the register 14. Out of all the 15 register, R14 is the link register. R0 is a normal general purpose register which is holding the value 12. Okay, so now let's see what is there in the PC pointing to. PC is pointing to this address, and in the address, what is the instruction present? SWI. And what is that? It is followed by some number. This is the interrupt number. 1, 2, 3, 4, 5, 6 is the interrupt number. When once it executes this instruction, it's an interrupt instruction. So what are the changes that will happen in the controllers? We will see here. What is happening? First thing, CPSR. What is happening to CPSR? So no, before going to CPSR, let me finish SPSR. So SPSR, there is a switching of mode. SWI instruction will convert the user mode. Presently we are in the user mode, it will convert into supervisor mode. So before going to that mode, you know about the modes. What will happen? Whatever is the status of CPSR, that will be loaded in SPSR. See here. So whatever the CPSR was there, it got moved on to SPSR register. Now what is the new value of CPSR? Everything is the same except one thing, I. I is becoming 1, means it is going to mask the other interrupt. Currently there is one interrupt getting executed, so other interrupts cannot be raised. That is the meaning of this. And now we are in the supervisor mode. It got changed. Now what is the PC content? It is holding the SWI handler, this 08 we discussed earlier, right? PC plus 8. So now PC is pointing to the address 8. We will see what is that. And LR is, what is LR? Link register always holds the address of the next instruction after SWI. What is the address of the next instruction? 8004. That is present in LR. And R not some value it is holding. So this is the status when once we execute SWI. So this was the old previous status. When once SWI was executed, this becomes the newer status. Let's proceed. Now, in this example, so we will take an example with a small code. So this is the explanation of the code. What will happen when once SWI with the instruction has happened? Actually, we will take this number and we will make a bit clear. We'll convert that into bit clear. So when once SWI is executed, the control will switch over to SWI handler. Here, we don't use the term called as ISR. We use a term called SWI. We'll use a term called as SWI handler. That handler will actually execute the ISR, the actual code, what has to be done. Now we will see how the entire process is executed with the help of an example. So this is the explanation. So before coming to the explanation, I'll just take off the example directly. Now that number was there. Now what is, let me just tell, this is the number, this is the number. So when once this number is executed, what is happening, we will see here in this slide. So it straight away comes to the SWI handler. So what does it do first? First thing, it will store the registers R0 to R12, general purpose registers, that contents it will store, and the link register. All these things will be pushed onto the stack, because now what this is the previous status. We don't know what is the older value of it, but right now in our handler, in our code, we will be using R0 to R12 link register. Everything we'll be using here. We don't want to lose the previous content. So first thing, we will push it onto the stack. We know which instruction to use. So whenever we are pushing the contents of the register to the memory, it is stored. So we are making use of STM, multiple registers. So there's a connection among all these topics, and we are making use of full stack. So it is pointing to the topmost element, and it's in the decreasing order. The addresses are in the decreasing order. Previous class, we have seen how the addresses gets decreased. The address will be, the stack address is given by SP. What are the contents we are pushing? R0 to R12 register. Overall 13 registers we are pushing, and LR. LR is the 14th register. So LR is R14. So LR is holding presently 8004, and R0 to R12, some values it is holding. All these things we will push it onto the stack. So since we are working with decreasing order, we know that the addresses, whatever we are having on the top, usually it will be the higher address. So I told LR is R14 and this is R12. Then it goes in the decreasing order, R11, R10. So first LR, that is R14 register, will be pushed onto the stack. Whatever the value is there in LR, that is pushed onto the stack. And then comes R12. Sorry, and then comes, it should be R11, R10, like that it proceeds. R12, R11, R10, it goes on till R0. Now, SP is finally pointing to R0. So this is the, it's in the decreasing order. Now SP is pointing to the topmost element of the stack, that is R0. So this work, we have pushed everything onto the stack. Now we will make use of the LR register contents. What is LR register contents? It is 8004. Now 8004 I'm subtracting. So what is the value? We'll get 8000. The contents of 8000 I'm pushing it to R10 register. So what is that? What is that 8000? What is the content present in 8000? The content present in 8000 is this number, 1, 2, 3, 4, 5, 6. That will be taken here. That number will be taken here. So we are extracting only that number. We want to know what is the interrupt number. We are taking that number. Now we will mask off top 8 bits. So here we have taken 6 bits only. Even if we take 7th and 8th bit, Okay, we have taken 6-bit. Even if we take 7th and 8-bit, we will mask that. How will we mask? Using this particular instruction called as uh, bit clear. This also, this how it works, all of you know. So what we are doing, we are taking R10. What is R10 holding? 1 2 3 4 5 6. Okay, that R10 is holding this 1 2 3 4 5 6. Okay, now what is the what with what we are doing bit clear ff 00000. So how the bit clear works? First it takes this number and it first performs one's complement. How it, what will be the newer value? It becomes 0 0. This ff becomes 0 0 and all the zeros will become ffffff. To that number we are going to AND. Bit clear works like that. We are going to AND R10. It is not add, it is AND, A-N-D, AND R10. What is that? 1 2 3 4 5 6. Whenever we AND any number with F, we are going to retain back the same number. So what is the number we are going to get here? 6, here 5, 4, 3, 2, 1. If at all we have other two numbers, that will be masked with 0. Any number you AND it with zeros, it will be 0 0 only. So we have masked the upper thing. So what is the actual number we got? 1 2 3 4 5 6. It is the actual address of the service routine. Okay. So now our 10 is holding the actual number. In this case, we don't find a difficulty. If we are adding other number, a 7th and 8th bit, then we will mask it. And whatever number we get, that will be our service routine number. So we are going to branch. BL means it is going to branch to that particular service routine whose address is this 1 2 3 4 5 6. So we are going to, whatever the code is there from this address till the end, it is going to execute that code. So for what the interrupt, whatever you have raised, the code is written in that particular address and is executed. And once everything is done, everything is over, we have to come back to the main program. How will we come back to the main program? We cannot come back. Before coming back, we have to pop the contents of the stack. This is the stack content. So how we are going to do? So R0 is the lower address data. So that will be popped to R0, then R1, R2, up to R12. And now whatever is there in the LR, that will be substituted to PC. Now what is the PC content now? 8004. So this makes the control to come back to the address of next instruction 8004 and it will resume. So what, to summarize, when an interrupt has arrived here at this point of time, what happened? The control went to that conversion process and it executed the SWI handler. After executing the SWI handler, the control came back to the next address after SWI and resumed the execution. So this is how the SWI instruction works. So this is what we have summarized in theory. So you know that R0 is just a value 12 that is used to pass between the main code and the subcode. So here the code called SWI handler is required to process the SWI call, and the handler contains the SWI number we discussed using the address of the executed instruction, which is calculated from the link register. We got it through the link register. And how that SWI number is determined, we will take that instruction, SWI instruction, and then we are going to AND NOT, means BIC. Bit clear is nothing but AND NOT with FFF00. So that we'll get the actual number to SWI number. And that is the actual 32-bit SWI instruction executed by the processor. And it shows the start of the following code. Whatever we discussed is the SWI handler implementation. And finally, the SWI number is placed in R10. So the load instruction first copies the SWI number into R10. The BIC instruction masks the top bits of the instruction, leaving the SWI number. So this is how the entire SWI instruction is executed.